Today, we're going to look at the second and final lecture of chapter number 9. And chapter number 9 talks about rotation of rigid bodies. The learning goals for today's lecture. The first one, develop relation between angular parameters, omega, alpha, used to describe rotation of rigid bodies and the linear speed and acceleration v and a for a point on a body. The second learning goal, identify moment of inertia of a rotating body about a fixed axis and calculate the moment of inertia of point masses about fixed axis. And the third objective, define the rotational kinetic energy in terms of moment of inertia. So let's start with relating linear and angular kinematics. Now we have here a shape which is not a regular shape, and it is rotating around point O. So actually it is rotating counterclockwise. So we can say the rotation here is about the positive z-axis. Remember what I told you, if you take your x-axis and y-axis on the screen here, the z-axis will be pointing, or the positive z-axis will be pointing out of the screen. Now this object that we have here, it's not regular, but we assume that the bodies are rigid. That means the points are fixed where they are. So let's take a point P here on the body. And this point P here will revolve around O. So I want you to consider two things here. Now the body is rotating. So we have a rotation about the axis around O here. So each point on this body will rotate through the same angular position theta, and it will have the same angular velocity omega, and it will have the same angular acceleration alpha. However, point P here will also revolve around O. So there is a revolution as well of point O here. And you can regard this point P as performing circular motion as well. And this is where we're going to find relations between linear and rotational or angular parameters. So now, if we look at point P here, and we look at what we call the angular distance, it will basically rotate through some angle theta. We can say that this is angular distance here, theta, that it goes through. Now, this point here, as it is revolving around, it will go through, or basically it will be the circumference of the circle. So we say here the linear tangential distance of that point, or any point on the body, it is expressed in terms of S, and S basically in meters, and S is equal to R theta. So if you choose a point here, for example, this point here will have a different R. And as it revolves around, S will be different. It will be smaller than this S here. And if you basically look at the circle here that it can make, and you look at the circle, you know that the circumference of this circle is smaller. So that's why you say here for a point on the body, okay, moves through, S is equal to R theta. Different points will have different S depending on how far they are from the center about which the body is rotating, but the point will be revolving. So we define S here as equal to R theta. So that's linear distance to angular distance. So angular distance is regarded as theta. The linear distance, which basically on the circumference of the circle here, will equal to r theta. Now, if we follow this definition, we can look at linear tangential, or what we call tangential speed. Remember, when we talked about circular motion in chapter number 3, we said in chapter number 3, we said we have two types of circular motion. We have uniform circular motion, in which the speed is constant, but you cannot say the velocity is constant because you're changing the direction of your velocity. And we talked about non-uniform circular motion. And in that, we said basically you need to change the direction of your velocity. And we talked about radial acceleration, which we said it's equal, or centripetal acceleration, which is equal to v squared over r. Now, we said this speed that we have here, it's what is tangential speed. And you need a tangential acceleration to change the magnitude of this. So now, if I look at my tangential distance here, and I want to get my tangential speed, v will equal to ds by dt. This is equivalent to saying it is d by dt of r theta from our definition, which will equal to r, because r is going to be fixed. It's not going to change as the body is rotating and the point is fixed from the axis of rotation at this r. So r is fixed. D theta by dt. And you know that d theta by dt is equal to omega. So this will equal to r omega. So your tangential speed here is equal to r omega. So the linear distance is equal to r theta, which is basically related to the angular distance. And the speed here, or the tangential speed, is equal to r omega, where omega is the angular speed. So we're relating linear to angular. Is this clear? Now, we also can change the magnitude of our velocity, which is basically the speed. We can change the speed, so we need an acceleration to do that. And the acceleration here, we're going to call it tangential acceleration. Remember, in circular motion, we talked about two things. We talked about radial acceleration, and we said this should equal to v squared over r, and that's responsible for changing the direction of your velocity. And tangential acceleration, which is responsible for changing the magnitude of your velocity. And then you will have your resultant acceleration. The resultant acceleration here should equal to a tangential plus a rad as vectors. So now, if I want to look at the tangential, well, it will equal to dv tangential over dt. And from the previous slide, we said that v is equal to r omega. So if you take this, r is not going to change. It's going to be fixed. So it will be r d omega by dt. And of course, this equals to what? Equals to alpha. So your a tangential here will equal to r alpha. So we said that s, the tangential distance, is equal to r theta, and v is equal to r omega, and a is equal to r alpha. S, v, a here are linear. Theta, omega, and theta, omega, and alpha are angular. So we have angular position, we have angular velocity, and angular acceleration. So that's how we relate these. So always keep this in mind. The body is performing a rotation around the axis, but every point on this body is revolving around the axis of rotation. It's like performing a circular motion. And we talked about two types of circular motion. So now, we also know that there is another component of the acceleration here, which we call radial component. It's centripetal, and it is always perpendicular to V, and this is what caused the change in direction. And we said it has a magnitude equal to V squared over R. But you know that your V is equal to R omega, so it's R omega squared, and of course you have R here. So that will give you R squared omega squared over R. So you can cancel this with that, and this is what you have, R omega squared. So for every point on this body, as the body rotates, there is an acceleration at that point, and that acceleration comes from the tangential acceleration, which changes the magnitude of your velocity or speed, and the radial acceleration, that it changes the direction. Now, as a vector here, if I want to get the magnitude, it will be, because since A tangential and A rad are perpendicular to each other, so you can take this as tangential, this is radial, so that's the this is the hypotenuse here. So A will equal square root of tan A tangential squared plus A rad squared. So you can say, well, this is equal to the square root of R alpha squared plus the A rad here is R omega squared, and square the whole thing. Now you can take R outside, so this will be R square root of alpha squared plus omega to the fourth. And that will give you the magnitude of the acceleration at any point on this body. Now, of course, if the body is rotating with constant omega, that means alpha is going to be 0. And you end up getting your centripetal acceleration only. Is this clear? Any question on this? So in this, basically, now we look at the relation between the linear and the angular. Let's take an example here. And let's look at example 9.4. An athlete whirls a discus in a circle of radius 80 centimeters. And 80 centimeters here, it's 0.8 meters. If you want to convert that to meters. At a certain instant, the athlete is rotating at 10 rad per second. So that's at a certain time. That's omega. Find the angular speed. And the angular speed is increasing at 50 rads per second squared. And this is basically your alpha here. At this instant, find the tangential and centripetal components of the acceleration of the discus and the magnitude of the acceleration. So that's your discus here. And we can take it from the center. Okay. Now it is rotating around this point here, which is about 0.8 meters. So your R is 80 centimeters, which is equal to 0.8 meters. The omega is equal to 10 rad per second. Alpha is equal to 50 rads per second squared. Now your tangential acceleration is equal to R alpha. So it's equal to 0.8 times 50, and that gives you 40 meters per second squared. That's how your angular speed is changing, which basically will translate also, you can get change in your speed. Now the A rad, which is the centripetal acceleration, which is responsible for changing direction, will be R omega squared, which is 0.8 times 10 squared, and that gives you 10 meters per second squared. So this disc has one acceleration, which is radial or centripetal, that causes change in direction, and you have a tangential, which basically increases the speed. And of course, when it leaves the hand of the athlete, will go with that linear speed. Now, the magnitude of the acceleration will be the square root of a tangential squared plus a radial squared, which is 40 squared plus 80 squared, and that gives you 89.4 meters per second squared. Is this clear? Is this clear? Okay, any question on this? Now, let's take another example here. And this is something where you have to be careful in designing propellers. You are designing an airplane propeller that is to turn at 2,400 RPMs, revolutions per minute. The forward airspeed of the plane is to be 75 meters per second, and the speed of the tip of the propeller blades through the air must not exceed 270 meters per second. So you have a propeller here, and it is rotating in air, and we assume that rotating bodies should be rigid, so point to stay with where they are, but they may deform, and they tell you here the maximum speed that you can have is 270 meters per second. You exceed this, something will happen to the propeller, and of course it will deform, and that of course will not serve your purpose. They tell us here what is the maximum possible radius that we can have for the propeller. Make sure that the speed cannot exceed 270 meters per second, and then what is, with this radius, what is the acceleration of the propeller? Now, we know that we have a forward speed of the plane at 75 meters per second. Now, the propeller having a 2,400 revolutions per minute. Each revolution is 2 pi, and we want to make it in minutes, so we have to divide by 60. So here you have 80 pi rad per second. That's basically your angular velocity or angular speed in rads per second. Now, you want to look at the tip of the propeller. The tip now has a forward velocity which goes this way at 75 meters per second, and it is rotating, so the tip is revolving around the axis here, and it will be rotating with the V tangential, and we said that this is equal to r omega, so you have to keep that in mind. So the velocity at the tip, and we take it as a vector here, it has the velocity of the plane going forward plus the velocity of the tangential at the tip, and note that we're taking these as vectors here because they are perpendicular to each other. As we say here, the V of the plane is perpendicular to the tangential. Now, if I want to look at the maximum speed at the tip, this maximum speed here will be, if I want to get the magnitude, and you have this vector where these are perpendicular to each other, it will be the square root of V of the plane squared plus V tangential squared. So it will be V of the plane squared, and the V tangential will equal to r omega. So it's r omega squared. So your V max here will be V of the plane squared plus r. Now I want, this will be maximum when r is maximum. So r maximum omega squared. The maximum should be 270 meters per second. Speed of plane is 75 meters per second. R max and omega is 80 pi squared. Now I can square both sides, so I will get 270 squared, and of course when you square the square root, you will get what underneath the square root, so you get 75 squared plus 80 squared, pi squared r max squared. The only thing that you don't know in this equation is the maximum radius, and the maximum radius here is 1.03 meters. With this situation here, the maximum radius that you can have, it's 1.03 meters. You exceed that, your propeller will be deformed. Now, in part B, with this radius, what is the acceleration of the propeller tip? Well, you know that your acceleration will have two components, right? It will have the A tangential plus the A radial. Now, in our case here, they tell us it is moving with 2,400 RPMs. It's constant. So that will give us alpha equal to 0. And you know that your A tangential should equal to R alpha. But since alpha is equal to 0, so that will equal to 0. So your A here will just equal to the A rad. And if you take the magnitudes, it will be A equal to A rad, and A rad is equal to R omega squared. Now we calculated the maximum radius, which is 1.03, and the omega is equal to 80 pi, so 80 squared times pi squared, and you get here 65,060 meters per second squared. That's a very high acceleration. You know that G is equal to 9.8 meters per second squared. And that's what makes things fall. Now look at this acceleration here. It's very high. And you know that F should equal to MA. So at the tip of your propeller, you have a very great force because you have a very big acceleration there. And that force that's pulling toward the center, if the tip of the propeller or the object there is not strong enough, it's going to be deformed. And that's why you have to be careful with this. Now, you can basically watch, and there are many on YouTube that they take DVDs or CDs and they start putting them on a drill, and then you can rotate them very fast, and then they break. They break because the force on each point in that is exceeding the force that is required to make that point in the CD or DVD. And that's why you have to be careful with this. Is this clear? Any question on this? All right. That's basically how we looked at linear and angular and relating the two. Here we're going to look at energy as well. When we have rotation, we also have rotational energy. So now, if we go back to the same diagram that we had previously, it's a regular shape, many points on it. So we can pick a certain point here. It's a distance r away, and it is the whole object is rotating. But this point here will go through a revolution, and it will have V tangential, which is equal to R omega. Now, the kinetic energy of this point here, if I can measure its mass, the kinetic energy, it's equal to 1/2 mv squared. And of course, V here will equal to R omega. But if you want to get the kinetic energy of the whole body here, well, the mass is distributed. It's not concentrated in one point. So what you do is you have to divide this into very small masses, and you have to calculate, because I told you each point will be at different R meaning different V. So if we do that and we want to calculate the total kinetic energy of this body here, and if we divide it into very small masses, it will be 1/2 m1 v1 squared plus 1/2 m2 v2 squared, and you continue like that. You can cut it into as many small masses as you can. Now, instead of using 2, 3, we'll use a subscript I here, and I here can go from 1 all the way to n, and n here could be the number that we have. 1/2 mi vi squared, where vi now is equal to ri omega I. But you know that the body rotates through the same theta, and it will have the same omega. So omega I will be the same, since omega 1, omega 2, so that's we have here omega. So if I go to my kinetic energy now, it will be the summation over I, 1/2 mi, and for V, it will be Vi, it will be Ri squared omega squared. And since omega is constant, I can take it out here. Half is out. This summation here of mi Ri squared, I will call this moment of inertia. And I'm going to give it the symbol I. So I here will equal the summation over I, where I is the number of representative points, mi Ri squared. So my kinetic energy now can be written as 1/2 I omega squared. And this is known as rotational kinetic energy. So when you have a body that is rotating, you can calculate a moment of inertia for that body. And the energy of that body, the kinetic energy of that body, is equal to 1/2 I omega squared. And that's how we did it. We started from the linear to get the rotational kinetic energy. In the previous slides, we looked at how we look at angular parameters, theta, gamma, and alpha, and how they are related to the linear quantities like distance and speed and acceleration. Is this clear? Is this clear? Any question on this? So now, how do we look at this moment of inertia that it came out of our math here? Well, moment of inertia measures the resistance to any attempt to change the rotation of a body. So for example, since we said the kinetic energy rotational should equal to 1/2 I omega, so I here is something that influences our rotational kinetic energy. And we define the moment of inertia as the summation over I mi Ri squared. So you look at the situation that we have here. This is your axis of rotation. This is the mass. You can measure how far is it from the on both sides, and then you can calculate. Now, when they're very close, R is small. So in this case here, you basically have a small moment of inertia. And if you rotate, you have a small moment of inertia, then you need small energy. So it becomes easy to rotate. But what happens if you take these masses now and you put them further? So this is Ri here, and this is another Ri, and you're squaring them. That will basically result in a greater moment of inertia. A greater moment of inertia, that means it will give you greater energy. And that's why you find it harder to rotate. And that's why we say here, moment of inertia measures the resistance to any attempt to change the rotation of a body. The bigger the moment of inertia, the harder it is. Is this clear? Is this clear? So let's take an example here to illustrate some of these points. And we'll start with example 9.6. A machine part consists of 3 discs linked by lightweight rods, like what we have here. we have mass A, which is 0.3 kilogram, mass B, which is 0.1, and mass C, 0.2. And they are basically connected by rods, 0.4, 0.5, 0.3, in this arrangement here. In A, what is the body's moment of inertia about an axis through the center of disk A, perpendicular to the plane of the diagram? So imagine if you axis which goes through A and it's coming out of the screen and you rotate this way. So you're basically rotating this way. Now, when you rotate, you have to look at moment of inertia. They told you ignore these rods here, lightweight. We're not to consider them. But now you have to look what are the axes of your rotation. So they tell you about A. So I will calculate my moment of inertia around A. And I know that it should be, by definition, I, where in this case, I will go from 1 to 3, because I have 3 masses, mi ri squared. Now, ma, and then I will put raa, that means how far is mass A from A, plus mb, rba, that means how far is A from B, plus mc, rca, and that means how far is C from A. Now, mass A, it's exactly at A, and that's why we said that's equal to 0. Plus mb rb A squared plus mc rc A squared. You get 0 here for A, plus mass B is 0.1. And how far is it? It is basically 0.5 squared plus 0.2 times 0.4 squared. And that's how far is it. You only concentrate how far is it from point A. And you calculate. Now, this basically will give you 0.057, and the units will be kilogram meter squared, because mass multiplied by R, and R has units of meter, but it's square them. So these are the units of your moment of inertia. It's kilogram meter squared. That's the moment of inertia around A. Of course, we ignored here these rods. We did not consider them. And that's why we said it is lightweight. So they're not considered in the calculation. Now, in part B here, what is the moment of inertia about an axis through the centers of disks B and C? So now you're looking through this axis here. You're rotating around this. So the same thing, if you want to calculate your moment of inertia, now we said BC here, that means around this line, BC. So it is MA, RA, how far is it from this line BC? MB, how far is it from BC? RB, BC. MC, and how far is it from the line BC? Well, B and C are on the line. So both of them, their distance is 0. But A here, it is basically 0.4 away from this line here. So it is 0.3 times 0.4 squared, and that gives you 0.048 kilogram meter squared. So moment of inertia is not the same for this. It's not the same value. It depends on which axis you're going to rotate. So there are different moments of inertia around different axes of rotation here. So you have to be careful with that. And we say that these are point masses here. We consider them as point masses. And we take their mass from the center, because things always are on the center of mass. Now in C here, what is the body's kinetic energy if it rotates about axis through A with angular speed omega is equal to 4 rads per second? You know that the rotational kinetic energy, and we put A around A, it's equal to 1/2 IA omega squared. And you already know that A from the previous slide. Okay. So you plug in 1/2 times 0.05. I think there is a 7 here if I'm not mistaken, but it's okay. Times the 4 squared, and that gives you 0.4 joules. So the units of kinetic energy, still joules. Okay. And this is now rotation. If you want to do it for BC, it will be different. Because if you want to get the kinetic energy R around BC, it will be 1/2 I BC times omega. So you're going to use a different I here, which is BC. And similarly, about any different axes, you will have to consider the moment of inertia around these axes, and then you calculate what you calculate your kinetic, rotational kinetic energy. Is this clear? Any question on these? So when you have masses connected by light rods, and you want to calculate the moment of inertia, you can do that basically around different axes of rotation. What happens if you do not have masses like this? You have an extended body, and you rotate around an axis through the body, or an axis that's basically touching the side of the body or something like this. How would you calculate the moment of inertia? Now that summation that we have, it will be basically go in integral. We're not going to do that here. I'm going to spare you this. But you will do it if you take second year courses and things like that. You will calculate the moment of inertia. But we'll look at certain shapes, symmetrical shapes that we can use. Now, if you use a rod of mass m and length L, and you want to rotate through the center of that, perpendicular to it, well, the moment of inertia here will equal to 1/12 ml squared. Now, if you want to rotate around the end, not through the center, well, your moment of inertia is different now. It's equal to 1/3 ml squared. So in the previous example, we looked at a way of calculating moment of inertia around different axes of rotation. Same thing here. You have a body and you want to rotate around different axes, you will have different moment of inertia. You have a rectangular like this, where you have sides B and A, and you want to rotate through the center of that. Well, the moment of inertia here will equal to 1/12 m A squared plus B squared. Now, if you want to rotate around, let's say, the axis A here, that will give you 1/3 mA squared. How about if you want to rotate, let's say, this way here, around this axis? Okay. So in that case, it will be 1/3 mB squared. Now, how about if you have a cylinder? And a cylinder, you can have a hollow cylinder. So you have an inner radius R1, outer radius R2. In this case, your moment of inertia around an axis that goes through the center of the cylinder, it is 1/2 mr1 squared plus mr2 squared. What happens if the cylinder is solid? Then it will be 1/2 mr squared. And of course, this is the moment of inertia there. How about if it is a thin-walled hollow cylinder? So what will be the moment of inertia here? Well, the moment of inertia here will be mr squared. So in these three different cases, if you keep the mass the same, you keep the radius the same, most likely you're going to find that maybe this one or that one will have higher moment of inertia. Now, if you have a solid sphere, the moment of inertia will equal to 2/5 mr squared. But if you have a thin wall sphere, like a ball, just have a thin wall, well, the moment of inertia is 2/3 mr squared. Now, we're not going to do this by integration, but we're giving you these different shapes, we're giving you the different axes of rotation, and what are the moment of inertia here. Now, if you're given this in a problem to solve an exam or in quiz, I will tell you what the moment of inertia is in terms of the symbols. Okay. But if you're doing a homework, you just have to go and look at these shapes and decide which one you're going to use in the calculation of your moment of inertia. Is this clear? Any question on these? Let's look at this example here. And now this will bring in how we deal with rotational kinetic energy. So we wrap a light non-stretching cable around a solid cylinder of 50 kilogram, diameter 0.12 meters, which rotates in frictionless bearings about a stationary horizontal axis. We pull the free end of the cable with a constant 9 Newton force for a distance of 2 meters. It turns the cylinder as it entwines with as it unwinds without slipping. The cylinder is initially at rest. Find the final angular speed and the final speed of the cable. So you're pulling with 9 Newton for a distance of 2 meters. The mass is 50, and they give you the diameter here, so you can get the radius, r, which is 0.12 divided by 2, which will equal to 0.06 meters. That's your radius now. Now, this will be rotating. Now, it's rotating because you're pulling, so you're doing work here. Remember what we did in chapter number 6. We said that the total work should equal to the change in kinetic energy. And change in kinetic energy is equal to K2 minus K1. But you're starting from rest. So K1 is equal to 0. Now they're looking at the final here, angular speed and speed. Now the work that you do, the only work that you see, it's done by this force here, which is 9 in Newton. You're pulling in this direction. Your displacement in this direction. The angle between both of them is 0. So it is 9, or the applied force times the displacement times cosine 0, and cosine 0 is 1. And the magnitude of your applied force is 9. The magnitude of your displacement is 2. This should equal to the change in kinetic energy, but the only kinetic energy you have here is rotational kinetic energy of this cylinder here. And this is a solid cylinder. So you can basically go back here, and the moment of inertia of solid cylinder is 1/2 mr squared. So the moment of inertia here will be 1/2 mr squared. So it's 1/2 times 50 times 0.06 squared, and that gives you 0.09 kilogram meter squared. That's your moment of inertia. The kinetic energy is rotational kinetic energy, which is 1/2 I omega squared. So it's 1/2 times 0.09 times omega squared. Now out of this equation, omega comes to be equal 20 rads per second. Now that's your angular speed. Now they ask us for the speed of the cable. The speed of the cable will be the tangential speed of this cylinder here, because you'll be pulling this way. So the speed of this cable, it's the same as this tangential speed here. And the tangential speed here is equal to r omega. And r is 0.6 times 20, and that gives you 1.2 meters per second. So when you have rotating bodies as well, you really have to consider rotational kinetic energy. Now in chapter number 6, we talked about the change in kinetic energy, where we said it's 1/2 mv2 squared minus 1/2 mv1 squared. But you don't have a moving body here. You have a rotating cylinder. So you consider the rotational energy as the change in the kinetic energy. Is this clear? Any question on this one? Let's take example 9.10 here. We wrap a light non-stretching cable around a solid cylinder with mass m and radius r. The cylinder rotates with negligible friction about a stationary horizontal axis. We tie the free end of the cable to the block of mass m and release the block from rest at a distance h above the floor. As the block falls, the cable unwinds without stretching or slipping. Find expressions for the speed of the falling block and the angular speed of the cylinder as the block strikes the floor. So situation A here, you have a cylinder connected by a cable to a block, and the block is a distance h away. And you release from rest. When you release from rest, the cylinder here is not rotating. The block here will start falling down, but it will start with v is equal to 0. So in this case, if you consider the energy of this situation here, where it should be equal to kinetic plus potential, you will find the whole energy is only potential, which is mgh, gravitational potential energy. Now, in the second case, when you release, the block will be falling down. Now, when it comes to hitting the ground here, well, in that case, you have linear kinetic energy for this block here, which is 1/2 mv squared, but also this is rotating, and it will have 1/2 I omega squared. And the potential will be 0. So all of your energy here will be kinetic. Here it's kinetic, here it is, here it's potential, here it will be kinetic. So we can look at conservation of energy here. We're going to look energy 2 should equal to energy 1 because the gravity here is doing the work. So you're going to look at your kinetic 2 of a block B and the kinetic 2 of your cylinder, we use a symbol C here, should equal to the gravitational potential of B when it hits the floor here. That should equal to E1, and E1 is the kinetic 1 of 1B, which is the block. B here stands for block, plus the kinetic 1 of C, and C here stands for cylinder, plus the gravitational potential energy of the block. Because C is fixed, it's not moving in terms of gravitational potential here. Now, the block starts from rest, so initial kinetic energy is 0. The cylinder is not moving, it's not rotating initially, so it's equal to 0. So the only energy you have is mgh. So your total energy is potential energy only. When it comes to the hitting the ground here, well, in that case, you have the kinetic energy of the block, which is 1/2 mv2b now squared, and that's v for the block, plus 1/2 I omega 2 squared, and that's the rotational energy of the cylinder. The potential energy of the block will be 0 because you can choose that y here is equal to what is equal to 0. You know one thing as well, that the speed of this block equals the tangential speed of the cylinder here. So this one here will equal to r omega, where omega is the angular speed of the cylinder here. So if you want to write your energy, it will be 1/2 here m r squared omega squared plus 1/2. Now you want to look at your moment of inertia here. And the moment of inertia here, it's equal to 1/2 mr squared. it should equal to the energy mgh. Now, if you multiply that by 2, you will cancel that half, and you have that half, it's cancelled as well. So what you have here, and of course this will be multiplied by 2, and that's why we have here as mg times r omega, r squared omega squared, because v is equal to r omega, plus I, where I is equal to 1/2 m r squared omega squared, equal to 2 mgh. The only thing that you want to get out of here is basically your omega now. Your v is equal to r omega. Once you know omega, you can figure out your v. So what you have here, you will have r omega squared will be multiplied by little m, the mass of the block, plus 1/2 the mass of the cylinder, equal to mgh. Now you want to get your omega, so you're going to take the square root of that. So here you can say that omega squared will equal to 1 over r squared times m 1 over m plus 1/2 m multiplied by 2 mgh. Now, if you want to take the square root to get omega, then you're taking the square root of 1 over r squared, which is 1 over r, and the square root of 2 mgh divided by m plus m over 2. And that basically will give you your angular speed here, which is omega. Now, if you want to get v, v will equal to r omega, and that will equal the square root of 2 mgh divided by m plus m over 2. Now, if you did this when we talked about conservation of total mechanical energy, and we told you that the pulley here is a frictionless, that means it's not rotating, you will find that v is equal to square root of 2 mgh, and you stop at that. And that's why I told you always assume that the pulleys are frictionless, so you don't consider them. But if they rotate, they will affect your speed. And the speed now, when the block comes here, it's not going to be the square root of 2 mgh. It will be the square root of 2 mgh divided by m plus the mass of the cylinder divided by 2. So you see a difference now. Is this clear? That's why in previously when we dealt with chapter number 4, 5, and 6, and 7, we always told you that neglect the mass of the ropes, the cables, whatever it is, and we told you the pulleys are frictionless. That means they're not going to rotate. But if they rotate, you really have to include them there. And that's one case where it shows you that. Is this clear? Is this clear? All right. Let's take a couple of questions here to try to reason with how we make this relation between linear and angular. You have something from a bike. You have the rear gear. You have the front one. The front one is bigger. And they want you here to compare the front to the rear. That's why they call compared, okay, to the rear. What will be the effect of the front? Now, we know that they're connected by a chain. The chain is going to have the same linear speed. You cannot say velocity because they have different direction, but it's the same linear speed, okay, or tangential speed. So that's why we say the VR here equal to VF. R here means rear, the back, and F here means the front. Okay. So we use this subscript. You know that V is equal to R omega. So the rear will be R rear omega rear, and the front will be RF omega F. Now you can take and you divide here by R rear, so you have omega rear will equal to RF by R rear multiplied by omega F. Now you know that the radius of the front gear is bigger than the rear gear. That means greater than 1. That tells you that omega R is greater than omega F. And that's why we say the answer here, if I compare the front to the back, they have the same linear speed. V is the same as I have here because it's the same chain, so they must have the same tangential speed, but slower angular speed because the rear will have a bigger angular speed. So the front will have a slower one, and that's why the answer here is D. So that's how we reason about this here. Is this clear? Any question on this? Good. Now, in this question here, you want to double the radius of a rotating solid sphere while keeping its kinetic energy constant. The mass does not change. To do this, the final angular velocity of the sphere must be. So they tell you you're going to have mass, it's going to stay the same. Kinetic energy is going to stay the same, but the radius is going to double. So initially you have R1, K1, R1, omega 1. Now here you have K2. R2 is equal to 2R1. They ask us of R2, but I know that the kinetic energy must stay the same. That's the condition that they gave us. So 1/2 I2 omega 2 squared should equal to 1/2 I1 omega 1 squared. Now I'm interested in omega 2. So omega 2 is going to equal to, if I want to get omega 2 here, will equal to I1 divided by I2 omega 1 squared. So if you take the square root of that, it will give you square root of I1 over I2 omega 1. Now, what is the moment of inertia for a sphere, solid sphere? It is 5 over 2 mr squared. So it's 5 by 2 mr1 squared for I1. For I2 is 2 over 5 m2r1 squared. The 5 of the 2 will cancel, the m will cancel, r1 will cancel, but you'll end up with a 4. So you end up with 1 over 4. And square root of 1 over 4 will give you 1/2. And that's why omega 2 here, it's equal to omega 1 over 2. And that's why we say that the answer here, it's going to be 1/2 of its initial value. If you keep the energy, kinetic energy the same, but now you basically change your moment of inertia, definitely your angular speed will change, and that's a situation here where we have to deal with. Is this clear? Any question on this? Good. Okay. I think we'll deal with this question here. You have 3 cylinders, and for these cases, you can look at the moment of inertia for each one of them. They want M and R to stay the same, and they want the same kinetic energy. Usually, you can have an incline like this, and they all come running down. This is H, so initially you have mgh, so they have the same initial kinetic energy, but when they get here, of course, they will have the same kinetic energy. So that's a situation that you can look at. Okay, so you start with the same potential energy, it will be the same kinetic energy at the end. But they give you a condition here where mass will stay the same, R will stay the same. If you make R stay the same, that means maybe you're using different materials here. And they ask you which one will reach faster. So you know that the kinetic energy should equal to 1/2 I omega squared. And since all of these kinetic energies are going to be the same, when they actually which one will reach first, or which one will be fastest? Well, it depends on the moment of inertia, because K should equal to 1/2 I omega squared. So omega squared here should equal to 2K divided by I. So the one with the smallest moment of inertia will be the one that have the bigger angular speed, and of course it will be faster. So if you look at these three situations here, you will find that the solid cylinder here is the one with the smallest moment of inertia. And if it's the one with the smallest moment of inertia, that means it will be the fastest rotating cylinder. And that's why the answer here is what the answer is, B. Is this clear? That's how we start reasoning here. We did a couple of examples just to show you. So in summary here, every point on a rotating object has the same theta, omega, and alpha. So you have an object that it's rotating, every point on that object through the axis that it's rotating will have the same theta, omega, alpha. However, V and A and S will be different, because S will equal to R theta, V will equal to R omega, alpha will equal to A will equal to R alpha. So the points that are closer will have smaller values than the points that are further. And this is where you really have to be careful when we talk about rotation and revolution. Okay, the whole body is rotating, but these points are revolving around the axis of rotation. Now, we defined what moment of inertia is, and we did it for point masses, and we said it's equal to summation over I mi ri squared. For different shapes, we gave you the results, but it could be done through integration and so on. And finally, we define rotational kinetic energy, which is equal to 1/2 I omega squared. Is this clear? Any questions on these? Any questions? Good.